All right, so here's where we were last time. We had defined this thing called the dot product. Here's the formula for it, for vectors in R3. Similar formula in R2. Similar formula in Rn. Yeah. Okay. I emphasize the notation. You have to put the dot there. It's not optional. Every year it seems like I have a student who just won't do it, and it's weird, and I count off points, and they keep not doing it. I don't understand. But you have to do it because there's another kind of product that we're going to see later today. And if you just write VW, it's not clear which product you mean. Right? So, like I say, not optional, you got to do it. Okay. Okay, we talked about these algebraic properties. Again, highly familiar looking, but I emphasize not actually familiar, right? I mean, you've never seen these before. These are brand new properties. And not everything that cosmetically looks like it looks just like what I saw in middle school or what have you. That doesn't mean it's true, right? So all of these deserve verification, and it's an easy exercise. I hope y'all will crank out, crank out one of them. Just make sure you get the idea of how those work. Okay, moving on to geometric properties. It's not hard to confirm. This one is surprisingly important, and also a little surprising. The dot product of a vector with itself is, here, let me get back up here. The dot product of a vector with itself, keep in mind dot product is defined by that algebraic formula, is the magnitude squared of that vector. Now I want to point out what I think is really weird about this. Dot product, you see up there, is defined algebraically. It's defined, not only is it defined algebraically, it's defined with 4-function arithmetic. Right? And yet what this geometric property down here says is that if you take a self-dot product, you get something that's intrinsically a geometric concept, right? Magnitude is intrinsically geometric. This is always an eyebrow raiser for mathematicians when something that's defined algebraically has a very natural geometric connection. That's interesting. Okay. All right. To be clear, magnitude squared, of course. Now, how surprising is this? I mean, after you get over the, weird, is it actually surprising that this works out? No, I mean, it's super easy to see this coming, right? Magnitude is the square root of the sum of the squares of the coordinates, so squared is just going to give you the sum of the squares of the coordinates, and you can really see that coming right there. Come on, right? It's easy to check, right? Okay. Here's one that's much more surprising, though. It's called the Cauchy-Schwarz inequality, and it says that any dot product, right, the absolute value of it will always be less than or equal to the product of the magnitudes of the two vectors. Now, what's more interesting, I think, about this one is that notice that this is any dot product. Not just some, highly, this is a very narrow concept here of a self-dot product, right? Okay, well, in this very narrow instance, then something cool happens. Okay, well, not impressive. This is any dot product. So, wow, that's cool, right? But on this one it is an inequality after all, so it's not saying exactly what the dot product is equal. It itself has a kind of a sloppiness in it, unimpressive aspect. But that said, I want to point out this little bit of cultural, also a little foreshadowing for those of you who are going to take Math 216. This still is worthy of a name. This is the Cauchy-Schwarz inequality. It's not just some obscure, fact about dot products. And the reason why is there are other versions of this result. This Cauchy-Schwarz inequality doesn't apply just to dot products. It also applies more broadly to I don't want to give anything too much away, but any kind of there's a certain category of an algebraic construction of which dot products are just one example. And the Cauchy-Schwarz inequality applies to all of them. So it's very, very impressive thing. So it looks like we have are you an enrolled student?
I am.
Okay, great. So I'm going to need some volunteer who is not enrolled to give up a seat. Is anybody here not enrolled in the class? Show of hands, who's not enrolled? Okay, can you, I'm sorry to, yeah. And yeah, if you want to grab a chair somewhere, you might be able to find one in a nearby room. Yeah, and I'm sorry for the tightness. Okay. Right, so now here's an even better, at least from a Math 212 point of view, even better fact about dot products. This applies to any dot product, just like Cauchy-Schwarz. But even better than Cauchy-Schwarz, this is an equality. So dot products equal, right, this formula here. And this formula is also, just like the others before it, entirely geometric. I mean, it's so weird that this algebraically defined formula for function arithmetic, right, has this remarkable feature that it computes a product of a magnitude and cosine of an angle, right? This is all big geometric talk here. So very surprising that these work out like that. It turns out it's easy to prove, by the way. So a real cute little proof. If you have a couple of vectors with an angle between them, notice you can look at their difference, v minus w, right? Don't forget how vector subtraction works. Notice that these three vectors make a triangle, right? And the law of cosines for triangles tells us that. By the way, if you're a little rusty on your trig, if you've forgotten your law of cosines, it's one of these things that it doesn't come up super often, but when it does, it's really handy. So it's a good fact to know. Anyway. Yeah, there we go, law of cosines. That said, now let's notice also, independent of the law of cosines, we can also take that vector and compute its magnitude squared by way of the formula from the previous page, right? Going back over here, one of the properties that we wrote down. A magnitude squared is a self-dot product. Right? So there we go. Magnitude squared is a self-dot product. We can take that self-dot product and we can FOIL that out. Now wait a second. Whoa, slow down. How do we know we can FOIL? That was a middle school thing, right? You can FOIL when you're doing algebra of numbers. These aren't numbers. Can we just assume that FOIL works? No, but we have algebraic properties that say that it does. FOIL is really just this distributive property combined with this commutativity. Right? So you can apply these properties a couple times, and out comes FOIL. And then, by the way, then you end up with some self-dot products, which of course are magnitude squared. So I'm deliberately glossing over those details. I encourage you to check me on that. But per FOIL, you can rewrite that as that. So now, we still haven't done what we wanted. We wanted to compute the dot product. We've done what I like to call a mathematical bank shot. This is a neat idea that sometimes if you want to compute something else. And then, having computed that same thing two different ways, the thing you're actually interested in shows up. And then you just solve for what you're actually interested in. And that's what's happened here. It's a real cool idea. This happens surprisingly often in math. If you want to compute something else. Anyway, we'll see some more examples of that as we go on through the course. Very clever move. So anyway, there's the result we were interested in. The dot product is computed with that handy formula. And by the way, this gives us an opportunity to show the Cauchy-Schwarz inequality. I'm going to point out, going back over here, if you take this equation and just take the absolute value of both sides, and then apply facts that you know about how, the absolute value of cosine theta, for example, is always less than 1, then out comes the Cauchy-Schwarz inequality. So, nice fact. Okay. Let me pause for questions. How are we doing? Everybody happy? Real easy example here. Notice that in this formula, you can solve for theta. Right? Thus giving you another formula. When you kind of relate, it's kind of the same formula in some sense. Very similar. So you can compute the angle between two vectors. And the algebra is not bad. It's a matter of, dot products and magnitudes, which are square roots, and then you're going to leave your answer as arc cosine of something. If you really need to know the actual numerical angle, if you're going to pull out the protractor and actually build something, then punch it up on your calculator, right? But the point is, this is a relatively easy calculation. And I want to point out this is a hard problem, right? If this were a two-dimensional problem, it'd be an easy problem. For any given vector, you can just tangent or whatever will tell you the angle off of some axis and just do that for both vectors and subtract. Right? But that's not what's going on in this example. In this example, we're computing the angle between two vectors that are in space. Right? So they're like this. So we're not computing a horizontal, just, know this angle and that angle and subtract, right? We're computing an angle that is tilted. And geometrically, wow, that'd be a really hard problem. Right? So the fact that the dot product crushes it is pretty neato. Okay. Another neat consequence of our formula that I can't quite fit on the page at the same time. So let me recopy it here real quick. V dot W, magnitude of V, magnitude of W, cosine theta. Another neat consequence of this is that knowing the dot product immediately tells you something very interesting about the angle between the two vectors. And it's a simple observation of the fact that this being a magnitude is always positive, and this being a magnitude is always positive. So that being the case, hey, if your dot product is positive, well, that means cosine theta has got to be positive. Right? And on the other hand, if your dot product is negative, then cosine theta is negative. And knowing whether cosine theta is positive or negative tells you whether the angle is acute or obtuse. So, neat fact, right? Dot product, super easy to compute, super easy at a glance to see if it's positive or negative, and therefore super easy to infer whether the angle between two given vectors in space is acute or obtuse. Neato. And then, of course, also if the dot product is 0, if that's a 0, then that's got to be 0, assuming these are non-zero vectors. Okay, and of course, cosine being 0 means you have a right angle. All right. Now, the disappointment about this last result is it is awkwardly. It depends very importantly on these vectors being non-zero vectors. So tragically, if you don't know what vectors you're dealing with, you have a couple of random vectors. You don't know anything about them. All you know is that the dot product is 0. Technically, you can't conclude that the vectors are perpendicular because we have to recognize the possibility. Look, that maybe that dot product is 0. Because one of the vectors is 0. Right? And in fact, if you think about it, if one of the vectors is 0, and here's a vector, and then here's another vector, if one of the vectors is the 0 vector, there isn't really an angle at all to talk about. Right? So it just wouldn't be right to say, oh, dot product of 0 means right angle. It's just not true. Right? There might be no angle. Much less not a right angle. Yeah, question.
It's just a 0 vector, just like a 0 and 0.
That's right. That's right. It has magnitude 0. Yeah. Right. It represents a displacement that I'm demonstrating right now. Not moving. Right? Yeah, totally. Do you have a question? Yeah.
Isn't cosine positive in the fourth quadrant as well?
Cosine positive in the what now?
In the fourth quadrant. When you're moving in a
Oh, well, yeah, sure. But if you look at the angle between, notice that whenever you have two vectors in space, you can always think of an angle between them that is less than pi.
Okay.
Yeah, so no, it's a good question, right? But geometrically, when we talk about the angle between two vectors, we typically mean the smallest angle. Yeah, totally. Right. Good questions. Thank you. So here's the situation then. Dot product is equal to 0. How do we describe that? We don't want to say, aha, so that means that we have a right angle, or that the first vector is 0, or that the second vector is 0, or possibly that they're both 0. This is awkward, right? So we have a term for this. The term is orthogonal. It's very convenient just to be able to say dot product is 0, therefore orthogonal. And you just have to remember that what orthogonal means. Orthogonal means, well, either they're perpendicular or one of the vectors is the 0 vector or possibly both. Okay. Oh my gosh, Siri thought I was talking to it. That's so weird. Let me put my phone over here then. Okay, so here's another reason we like this term. It turns out, I mean, you look at these two equations and you think this is a tool and this is a conclusion. I mean, this is something that we're actually interested in. I want to know when we have right angles, right? And dot product is just a tool to get me there. You'd be surprised, but it turns out that sometimes what we're actually interested in is, I mean, believe it or not, we'll see some examples coming up probably Wednesday. Sometimes what you want to know is it the case that these two vectors are either perpendicular or one of them is the 0 vector? Sometimes that's what you want to know. So sometimes orthogonality is the more interesting concept. This is not the consolation prize to the right angle. Sometimes it's the prize. So anyway, we'll see an example of that on Wednesday. Hopefully Wednesday. Anyway, certainly sometime soon. Okay, so easy example. Here's a couple of vectors. Are they perpendicular? Well, they're obviously not 0. And these two vectors, their dot product is easily computed to be 0. So, yes, these vectors are perpendicular. And that's easily checked also by actually just drawing these vectors. Now, notice these vectors are in R2. So, super easy to actually confirm that, yeah, that's a right angle. Okay. While I'm here, let me also point to a neat trick that this is highly suggestive of, and that is that if you have a vector, and if you want to find another vector perpendicular to it, correction, if you have a vector in R2, and you want to find another vector to it, another vector perpendicular to it also in R2, just switch the coordinates and add a minus sign, and that'll do it. Neat little tool, right? Add this to your toolbox. You never know when this might be exactly what you need. Find a perpendicular vector in R2. Okay. So let's talk about some applications. We've seen some connections of dot products to geometry. And that's nice and all, right? But let's, what else can you do with this? Component is a great answer to this question. If you find yourself looking at a vector and you're not interested specifically in what the magnitude of the vector is, but you want to know, okay, so not how far the vector points, but specifically how far does the vector point in a certain specified direction, right? So this is the direction along which I'm interested in movement, and I don't really care about how much this vector points somewhat that way. Don't care. I'm not interested in that direction. I'm interested in this direction here, right? So I want to know what is this length? How far does the vector point in the given indicated, direction of interest? So maybe this is, we're playing football, right? And the ball was here, and then there's a pass, and then the ball, the tackle happens here. How many yards did you gain? You didn't gain this many yards. You gained that many yards, right? If we're talking about forces, sometimes we want to know how much of a force is pointing in a particular direction. We're going to see that on the very next page. Details to come. But component in a specific direction could be very, very important. So how do you compute a component? Neat fact, this triangle you see here, right? I can talk about the trig of that triangle, and there you go. The component that I'm interested in is hypotenuse times the cosine of the angle. So, flashbacks to high school trig, right? I hope everybody remembers all that stuff. Okay, so magnitude, the hypotenuse there times cosine of the angle. Having written that down, another little clever move that very useful in math sometimes, I'm going to multiply and divide by the same thing, because that's legal, right? I'm multiplying by 1. That's basically just a 1 that I'm multiplying by. Having done that, notice that my numerator is now exactly the dot product, and we have ourselves a very compact and convenient trigless formula for how to compute components. Right? I don't have to measure an angle and then compute the cosine of that angle. I can just compute a dot product with 4-function arithmetic. So, sweet. Right? Okay. Another way to say this is that I've taken advantage of the fact that components and dot products are both computed with the same cosine of the same angle between those two vectors, and so therefore, thus the sort of the nice connection. Okay. All right. Yep.
So for this one, you're not actually creating a new vector, like when you get an answer, magnitude, it's just a number, magnitude.
Yeah, that's right. So great question. So component is a number. That's right. It is a scalar valued thing, just a number. Yep. You can. It depends on the book you're reading and the usage. Sometimes people will talk about this vector and call it the component. Sometimes it'll be called the projection, the terminology. The context should always make it clear. But as I'm using it here, yes, scalar, absolutely. Yeah. Okay. So, while we're here, let's notice if you have a unit vector. The magnitude is 1, and you get this really nice punchline that components are dot products with unit vectors. Neato. Very important fact to remember about unit vectors. Unit vectors have this shocking feature that dotting with a unit vector computes a component in the direction of that unit vector. And we're going to use this a lot, by the way, when we get into, especially when we get into chapter 15. Lots of this. And non-trivial amounts in chapter 13. Okay. Oh, and while we're at it, let me just also point out, notice that when we're computing the component in the direction of a not unit vector, notice you're still dotting with a unit vector. Right? It's still dotting with, there it is, W divided by its own magnitude. That's the unit vector pointing in the direction of W. So, okay. Alrighty. Okay, so let's do a little bit of physics. I hope you all remember some high school physics. If you don't worry about it. Not a problem. But there is this concept called work that we represent with W, and think of it as the amount of effort that it takes to accomplish a task. The units of work are energy. You can also think of work literally as the energy that it takes to accomplish a task. The problem there is, of course, energy is another physics concept. So I'm trying to make it a little bit more relatable. Think of it as effort. Right? So force times displacement. And a standard fact from high school physics gets written like this a lot. And this representation of the formula is awkward. It's because you have to put this asterisk down here. It's not just force times distance, full stop. It's force times distance, asterisk, with the understanding that we're talking about the force and the displacement being in the same direction. And if they're not, then, well, I have to consider just the amount of the force that's actually in the direction of the displacement. So the awkward, right? Okay. Well, that component of the force that we actually care about, we know how to compute components now. Formula on the previous page, right? A nice real-world application of components, which is an application of dot products. So this is, by extension, an application of dot products. The amount of work that it takes, I'm going to look at the distance, sure. Right? How far did I go in that displacement? And I'm going to multiply by not the magnitude of the force. No, that force vector is going the wrong direction. I don't care about that force vector. I care just the extent the force is moving, the extent that the force is pointing in the direction of the moving. Okay? So the component of the force. And of course, we know how to compute components at this point. Components are computed with dot products like that. Notice as well that displacement, well, that's the magnitude of the displacement vector. And lo and behold, check it out, those cancel. And we get this very elegant little result here, and that is that the amount of work accomplished, or the amount of work that it takes to move a certain displacement while exerting a certain force, even if the force is not moving in the same direction. Dot product. Force dot displacement. That's pretty neato. I mean, the dot product makes that asterisk go away. Right? The dot product automatically accounts for the fact that, well, the force might not be in the same direction as the displacement. So, right, gone. Lovely. By the way, let me point out something else about this. You come back up here to this our initial formula. We could have made the complaint right away that, look, this formula stinks for another really big reason, and that is that forces are not numbers. What are you doing representing a force with a scalar when the very first thing that we did on the very first day of actually talking about Math 212 material was give examples of vectors, and forces was like our third one. Right? Forces are vectors. They have directions. It's not a number. Why are we representing as a number if it's not a number? Weak. Right? So likewise, displacements. That was our very first example of a vector. That's a vector. What are you doing representing that as a number? Right? Lame. So right off the bat, this formula has the nice feature that it is recognizing forces as the vectors that they are, and displacements as the vectors that they are. So it's just right and proper that we should want a formula involving those vectors. And then the dot product is the rest of the story. So, neat fact. Okay, so new topic. We're going to talk about the other product now. We're going to talk about something called cross product. The reason that we have to be all particular about terminology and notation with vector products, the fact that there are two of them. So it's going to take me a while to actually work up to the formula for cross product. It's weird. It involves objects that we have not defined yet and need to have a good handle on in order to be able to I want to be able to make sense out of cross product when we get to it. So I need to develop some tools. So it's going to take several pages of other stuff before we can actually write down that formula. So bear with me on that. We're going to talk about determinants. Now, I know some of y'all have seen determinants before. That's great. I may be showing you more than you've seen about determinants previously. I don't know. Who knows? What I'm going to show you about determinants, by the way, is a lot less than we're going to talk about determinants in Math 216. For those of you who take Math 216 and likewise 221. And in fact, just so you know, what we do with determinants in Math 216 and Math 221, also not all that there is to know about determinants. Determinants are actually really deep water. It's really heavy. There's a lot of weird, sophisticated ideas that are involved with determinants. So I just want you to know, what we're doing. So we're boating around, and just FYI, we're over a really deep Pacific trench. You can't tell from the surface, but still kind of cool. All right. Okay, so I'm going to start off by talking about neither of these things. I want to talk about orders, how to order vectors, and look, at a glance, it looks like a silly question. Here's a couple of vectors. There's a vector. There's a vector. So I have the same two vectors. I've written this pair of vectors twice. And notice there's two different orders that I could label them. I could have the green one be first and the purple one second. Or I could have the purple one first and the green one second. Now, why we would want to do such a thing, we'll talk about that later. But let's just take it as a given, and we want to be able to talk about orders, the different ways that you can order vectors. Now, how would I describe these two orders? I don't want to do it by color, right? Because that's arbitrary. I pick those colors out of a hat, right? I don't want to do it like alphabetically by the name. of the like if I call them V and W, I don't want to say, well, we have alphabetical order and not alphabetical order, because again, those are arbitrary labels. So I would like to come up with some idea of something that's intrinsically geometric to distinguish these two orders from each other. And one thing that you might run to, a lot of people do, is say, okay, well, we could talk about left to right or right to left. And, you can do that. It just ends up, it's kind of arbitrary for one thing. I mean, turn your head to the side and all of a sudden right to left maybe becomes left to right. It's just, there's something arbitrary about that. Likewise with top bottom. So there is something arbitrary. Perspective is arbitrary, though. So what I want to point out is that a good answer to this question is to use the notion of clockwise and counterclockwise. If first to second goes like that, you call it a counterclockwise order, because going first to second, you're going counterclockwise. Whereas here, first to second, clockwise. Turn your head to the side, doesn't change a thing. Now again, this is arbitrary, right? But there's something kind of natural about that. Okay. All right. So what we're going to try to do now is come up with a sort of a three-dimensional version of this, right? What is a three-dimensional version of clockwiseness, counterclockwise-ness, right? So if I have three vectors in space, three vectors in R3, is there I could order these three vectors. I have three vectors, right? I could order them in any of 6 different ways. How should I talk about those geometrically? Right. So there's a good answer to this question. It's big surprise. It's going to be a geometric conversation, so I'll be doing a certain amount of hand waving, but pretty literally. But we're going to use the human right hand. This is arbitrary. The person who came up with this idea must have been right-handed. But here's the idea. Whichever is the first vector, point your index finger of your right hand in the direction of that first vector, whichever one you're calling first in your order. Now, I don't, at this moment, care about what you do with the rest of your hand, right? As long as that index finger is pointing along that first vector, cool, right? So there's lots of different things that you can do with your palm, if you will. Okay. That said, orient your palm now in whatever way is necessary to get your middle finger to bend toward and be pointing in the direction of the second vector. Now, notice, right, depending on where that second vector is, I might have to do it like this, or I might have to, or maybe even, be careful, don't make any rude gestures. Okay? But the other thing that you have to keep in mind is when I say bending your middle finger, right, toward that second vector, only bend the middle finger the way fingers want to bend, so please don't do any hand yoga, right? Okay, so index finger has to stay parallel to your palm. That's one of our arbitrary rules. Index finger along the palm, parallel to the palm. Middle finger bending the way the middle finger wants to bend. And what you'll find is there's really only one way that you can take this hand gesture here, and index finger on the first vector, middle finger on the second vector. There's really kind of only one way to do it. Okay. Now notice, having done this, these two vectors define a plane. There's a unique plane through the origin, let's say. That's parallel to those two vectors. Right? Okay. Notice as well, your thumb of your right hand points on a clear side of the plane. And again, no hand yoga, right? So thumb's doing what thumbs want to do. Your thumb points on a well-defined side of that plane. So here's the thing. Index finger, first finger. Middle finger, second finger. If the third vector points on the same side of the plane as your thumb, then we call that ordering a right-hand order. But if that third vector points on the other side of the plane from your thumb, then we say that is not a right-hand order. And now let me appeal to your geometric intuition. The thumb here of my right hand is defining the side of the plane that is the right-hand order. What should we call it if it points to the other side? I have a proposal. Index finger Middle finger bending the way middle fingers want to bend. Notice that my left hand thumb points to the other side of that same plane. Oh. Right? Let me just do this. Okay, so that third vector is either on the right-hand side or what I'm going to call the right-hand side or the left-hand side. And so I'm going to call those orders right-hand order and left-hand order. Okay. All right. There are, of course, some anomalous, exceptional cases. So, for example, even in 2 dimensions, right? What if the two vectors are parallel? Is this clockwise or counterclockwise? Well, neither. Okay, so I mean, yeah, sometimes there are no good answers. What if one of the vectors is the 0 vector? Well, yeah, okay. So again, sometimes a pair of vectors is neither clockwise nor counterclockwise, and likewise with right-hand order. Sometimes first vector, second vector. Here's the plane that they define. Sometimes that third vector might be 0, or it might be one of the original vectors, or parallel to one of the original vectors, or it might be just parallel to that same plane, right? So again, there are exceptions where it's neither right nor left-hand order. Usually not. Okay. So this is kind of what I like to call a 3D analog of clockwise-ness and counterclockwise-ness. It's the notion of right-hand order versus left-hand order. Pretty clever idea. Just like clockwise, counterclockwise, there are mirror images of each other, right? I mean, if anyone's ever looked in the mirror and looked at the clock behind you, it's backwards. Likewise, if you take a right hand and look at it in the mirror, it looks like it's that image person's left hand, right? Right and left hands are mirror images, just like clockwise and counterclockwise are mirror images. Okay. Some other neat facts. This is kind of neato, but when you cycle a listing of vectors, and keep in mind we're talking about an order, right? We represent an order by representing them in a list. The list implies first, second, third, right? So when I write A, B, C, this is a list that implies an order which is therefore either right or left-handed. I don't know which. But even though I don't know whether, if I just write ABC, right? I don't know if ABC is right or left-hand order, but I do know that if I take that A and if I move it over to the other side, like so, thus cycling the order, the handedness is the same. This is pretty weird. But ABC and BCA, always the same handedness. They're either both right hand or both left hand. I don't know which. There's an easy little hand gesture demo of kind of, in some sense, if you will, why this is true. Here it is. This is a good thing to think through, right? But first, second, third. Now here's those same 3 vectors. The one that had been third, I'm now saying is first, per the cycling, right? First, second, third. And look at that, they're both of these arrangements of my right hand, they're both with my right hand, so same-handedness. Everybody see how that works? I think this is really clever. It's really satisfying. So this little hand gesture is why that's true. Or, if it's left-handed, like this. Another neat fact, if you trade 2 vectors, so notice here I'm trading B and C, that will always change the order. So in other words, these 2 listings here, ABC and ACB, always have opposite orders. And that's another little hand gesture game, and you can think it through on your own. Look, so let's suppose this is ABC right here. A, B, C, right? Apologies to those watching on the recording. It just, but A, B, C, right? If I were to switch the order, keep in mind that's A, that's B, that's C. If I were to trade A and B, now I'm about to commit a little crime here. I'm going to actually do this And you're not supposed to do that, right? I just broke the rules, right? But just for ABC purposes, right? A, B, C. If I want to rewrite the order as B, A, C, well, notice that's not right-hand order anymore, but it is left-hand order. So it's pretty intuitive, I think. Pretty satisfying. Okay, moving along. Let's talk about determinant a little bit. I think everybody here has seen determinant, at least a little bit. If you haven't, no sweat. I'm going to tell you everything you need to know about determinant. If you have a 2x2 matrix, like so, the determinant of that 2x2 matrix is this little formula. It's AD minus BC. And a lot of people remember this formula by, well, you sort of go down the diagonal and then subtract going down the off diagonal. Or if you prefer, kind of like that. Anyway. Okay. That's the formula for determinant. Easy formula to write down. Now let me tell you what's not easy. This is the deep water. Right? This is the, oh my gosh, it's really far down there. Why is this? Why did someone choose this to be the formula for determinant? That's heavy, as it turns out. Okay. But this little formula and variations of it that we're about to see, it turns out they have some remarkably natural geometric properties. It's very weird. Okay. Here's the formula for a 3x3 determinant. This is quite a bit weirder. There it is. There's your 3x3 determinant. Why? Where did this come from? Why do we care about this thing? Well, heavy question, but it turns out that this has some remarkable properties. And again, proving these properties is depending on how you do it. I mean, by the way, you can prove these properties with basic techniques. It is true. I mean, I can prove these properties with, or some of the properties I'm about to show you of determinant with just like high school trig and such, but they're ultimately not very instructive, and they're a distraction from what really the better arguments are, which are very deep. Okay, now nobody can just memorize this formula. It's too weird, so let me show you the pattern. The pattern is we are in some sense kind of going along the top row. Notice the top row entries right there. For each of those entries in the top row, let's start with that one. Notice we are crossing out the row and column that it's in and then looking at the 4 remaining elements, which is a 2x2 matrix, and taking the determinant of that 2x2 matrix. That's the pattern. Notice the next term, same deal, going along the top row, recall. Cross out the row and column. Look at the remaining 4 elements, and here it is. We're taking the determinant of that submatrix, they call it, multiplying by that element in the top row. That's a weird little formula. Again, no one would just sort of naturally... I mean, you could almost imagine the formula for the dot product. Maybe writing that down or something. But no one would just, hey, how about this? I wonder if this is interesting. Right? It's too weird. Let me call your attention, by the way, to this minus sign. Very easy to forget that minus sign. It's also very, very, very important. Likewise, that minus sign. Don't forget those minus signs. They are what makes it work. If you don't use that minus sign, you'll get wrong answers. But you'll also be writing down a formula that is not at all algebraically natural. Now you're just writing down a weird formula for no reason. Right? So, very important to remember that minus sign. And it's so easy to forget because you tend to be distracted. You're like, okay, go across the top row, and I gotta take these numbers, and which ones do I put over here, and then I gotta do the determinant. There's other things going on, and it's easy to just oops the minus sign. Please be careful. And don't oops it. Okay. All right. So now I'm going to try to tell you some interesting facts about these constructions. We're going to start off with the 2x2 determinant. here. And here's a wacky fact about the 2x2 determinant. Suppose you've got a couple of vectors, A and B. Now, it's just two vectors. Notice this is an ordered list of vectors. So A is first, B is second. Just an observation. Okay, now, there's a couple of things you can do with these two vectors. Suppose I were to take these two vectors and draw them geometrically. And notice that once you have two vectors, you can extend and make the corresponding parallelogram. Free country, you can do that if you want, right? Now here's another thing you can do with those two, unrelated, seemingly. I'm going to take these same two vectors, A and B. I'm going to take the first vector, I'm going to make it the first row of a matrix. I'm going to take that second vector and make it the second row of a matrix. Now, again, with the free country, right, you can do that. But the big question comes up, why would we want to... Are we just making stuff up now? Where is this going? What does this have to do with anything? So is there a relationship, I want to ask rhetorically, is there a relationship between that matrix and this parallelogram? And it turns out it's a very strong relationship. It's hard to see this coming. But neat fact, the area of the parallelogram is always equal to the absolute value of the determinant of that matrix. So that's a strong connection there. Determinant tells you area. Now let's just take a moment. All right, let's come back up here. Wait, we talking about this little weirdo? This arbitrary, with the minus sign and everything? That formula computes areas. Yeah. Does. It's very surprising, but true fact. Determinant computes area. Now I emphasize with the absolute values, right? So determinants can be negative. I'm not saying that areas are negative. No, of course not. Area is an intrinsically positive thing, like distance is an intrinsically positive thing. So it's the absolute value of the determinant that will always give you the area. Okay, now. When you take the absolute value, it kind of feels like you're throwing away the sign, right? Let's think instead of something else you could do with that sign. You could look at the sign itself, that the plus or the minus of that determinant, and that tells you the order. Let me add a notch here. That tells you this order. That tells you whether that's clockwise or counterclockwise. Positive means counterclockwise. Negative means clockwise. So this whole thing here entirely described by whether the determinant is positive or negative. It is weird that these are true. I mean, shockingly geometric facts about this weird little weirdo formula. Okay. All right. So let me give you an example of this in action. Let's see here. Here you go. So here's a couple of vectors. First vector, first row. Let's draw it on the picture. Second vector, second row. Draw it on the picture. Notice that in computing the determinant here, that determinant, its absolute value is 5, and that tells us that area. Which is cool. Notice the minus sign there. That's negative. That is our algebraic evidence that this is clockwise. Yep.
But you could have seen that it was clockwise.
Oh yeah, in this case, lucky break. Yeah, I mean, so one thing I like to do very often is take tools that allow us to draw conclusions and apply them to situations where we already know the answer. It's a sanity check purpose, right? I mean, so we know that the formula got the right answer, and that's therefore persuasive about the formula. But no, you're quite right, of course, in this case. Yeah, right. But very often you can't. Very often it's hard. Well, in R2 it's actually always pretty easy. But there's going to be a 3-dimensional version of this where it's not always going to be obvious. Yeah. Okay. All right. So what is that 3-dimensional version? We've got all the tools that we need here. So, wait a second. Oh gosh, I'm out of time, aren't I? That's too bad. Okay. Well, we're going to quit right here for today, and we'll pick up here on Wednesday. See you then.